So myself, Dr. C.R. Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So we are going to discuss about the laser glass spectroscopy. Under the laser glass spectroscopy, we are going to discuss about the today topic name is spectroscopic behavior of terbium-3 plus ions in zinc phosphate glasses for green laser applications. So today we are going to discuss about the terbium-3 plus ions doped in the zinc phosphate glasses for green laser applications. This is the today name of the topic. So last and previous session was discussed about the optical properties of europium-3 plus doped lead fluorophosphate glasses for the applications of red laser applications. That introduction, experimental methods, and present discussion conclusions of the last section we discussed about the europium-3 plus doped lead fluorophosphate glasses. So today outline of the today talk is on the spectroscopic behavior of terbium-3 plus ions in zinc phosphate glasses for green laser applications. First introduction. In introduction, we want to discuss about the rare earth doped glasses and also terbium-3 plus particularly and phosphate glasses. Next, experimental methods and techniques for the terbium-3 plus doped zinc phosphate glasses. Next, result and discussion of the spectroscopic properties of terbium-3 plus ions in zinc phosphate glasses. Next, finally, conclusion or summary of the terbium-3 plus doped zinc phosphate glasses. Next, coming to the first introduction, motivation and rare earth elements. Main motivation of the rare earth elements. So this is the periodic table of the rare earth ions. See the lanthanide ions are rare earth ions. This is belongs to the F black elements. F to F transitions from starting from atomic number 58 to 71. So that is cerium to cerium, prismodium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, yttrium, lutetium. These are the 14 elements of the rare earth ions or lanthanide ions. In these 14 elements, today we are going to discuss about the terbium-3 plus ions. That is the atomic number of 65 and atomic volume is 157.9. So this we are going to discuss about the today topic is terbium-3 plus ions doped zinc phosphate glasses for green laser applications. Next, coming to the importance of lanthanide ions. What is the importance of lanthanide ions, particularly in the case of terbium-3 plus ions? See, this is the 14 elements of the lanthanide or rare earth elements. Among the 14 elements, we are going to discuss about the particularly terbium-3 plus ions. So this terbium-3 plus ions mainly is F black elements. So shielded of 4f orbital because electronic configuration outermost electron will be 4f black orbital elements. So that is why it is shielded of 4f orbitals. Has similar chemical properties and electrostatic bonding and variable geometry. These are the importance of rare earth elements. Next, particularly, what are the important applications of the rare earth elements or lanthanide ions? So, fascinating optical properties are the having of the lanthanide ions, particularly luminescence from F to F transition, because this is belongs to the F black elements. That is why each and every transition comes from the F to F transitions. Next, characteristics of emission for each ion. Next, narrow emission lines, high chromatography purity. Next, emission color is not very dependent on the ion's environment. Next, large Stokes shift means Raman shifts is having the large. Next, direct excitation in 4f levels is not efficient. Next, sensitization luminescence is prepared. Next, finally, log excitation states lifetimes. So, if you see these are the fascinating optical properties of the lanthanide ions or rare earth ions. In particularly, in terbium-3 plus ions, it's having the longer lifetime. At the same time, electronic emission cross section should be also more. So this we are going to discuss about the today. If you see in this graph, this is from thulium, terbium, dysprosium, europium, samarium. These are the different kind of rare earth ions. See, if with terbium ion, it shows the green emission. So terbium-3 plus ions showing the green emission in the visible region around 545 nanometers. If you see the europium is having the red emission. Samarium also around deep red emission. These are the visible emissions of the blue to NIR range. That means we are getting the energies from blue to, that means blue shift to in a near infrared region. So here some different near infrared region wavelengths, that is ytterbium, neodymium, erbium. These are the from starting from 800 nanometer to 1600 nanometer. So these are the different rare earth ions and its emission intensities. This is the importance of the lanthanide ions. Next, coming to the introduction, that is rare earths. What is the mainly importance of the rare earth elements? So 4F and 5F black elements and their unique travalent state of 4Fn electronic shielding by 5s to 5s6 electrons and so many advantages, because rare earth ions all belongs to the 4F configuration. That 4F electrons will be shielded by the 5s2 and 5s6 electrons. This is the outermost electron configuration of the black elements. Next, what is the importance of glasses? Glass is an indispensable photonic platform material due to its high optical transparency. So, glass material, it exhibits the highly transparency, at the same time thermomechanical strength and the ability to be shaped into almost unlimited range of geometrical structure and compositions. So these are the important properties of the glasses. Next, what are the important applications of the rare earth elements? So laser gain media. So it is rare earth doped glass materials having the laser gain media and fiber amplifiers and optical components and medical accessories and massive structures and entertainments. So these are and etc. These are the different kind of applications for the rare earth doped glass materials. Mainly it can use for the fiber amplifiers and optical components and medical devices and large gain media. That's a laser gain media. That means laser properties, we can study the different kind of rare earth ions. So rare earth ions in glasses. So many applications, particularly laser gain media. So laser gain media is one of the important prominent properties in the rare earth elements whenever doped with the glass materials. Next, optical fiber amplifiers. So optical fiber amplifiers also we can use for the different kind of applications in the particularly glass materials doped with rare earth ions. Next, coming to the rare earth elements main introduction. Among several possibilities, Re3 plus rare earth doped materials classes are of the special interest for the active display and image processing panels due to their transparency, easy shaping, and cost-effective properties. This is one of the important ones. Highly transparent, optically highly transparent, easy shaping, and cost-effective. And also economically, it is cheap. That is the very important properties of the glass materials doped with rare earth ions. Next, particularly phosphate glasses. So coming to the our host glass is the phosphate P2O5. Have attracted much attention given their unique physical properties such as high thermal expansion coefficient, low melting and softening temperature, high electrical conductivities, and extensive UV transmission. So it will extend to the ultraviolet transmission. These are the important properties in the particularly for the phosphate glasses. Now coming to the zinc phosphate glasses. In zinc, the zinc is used as a modifier in the phosphate glasses, have been used in optical waveguides and solid state lasers as well as soldering and welding between the glassy materials and metallic parts, the electronic circuits and television tubes. So these are we are using for the zinc phosphate glasses for the important applications of the zinc phosphate glasses, because their thermal expansion coefficient is similar to that of the many metals. So if we compare to the different kind of metals, in zinc phosphate glasses, thermal expansion coefficient is very similar to the different kind of materials. That is why you can use for the different applications for the zinc phosphate glasses. Next, coming to the introduction of the network intermediate aluminum Al3 plus and network modifier zinc Zn2 plus induces structure changes in the phosphate glass structure formation of non-bridging oxygen, NBO oxygen, that is non-bridging oxygens. So these are the important parameters for the terbium 3 plus zinc phosphate glasses. Next, coming to the material selection. So in this present work, we are using the material composition. What kind of materials are used in the present study? See here, the present material section highlights the facts, advantages behind the selection of phosphate glass system for the present study. The particularly in the spectroscopic properties of terbium 3 plus dope zinc phosphate glasses for green laser application. This is our main topic. In this, what kind of chemical composition is used to prepare the zinc phosphate classes? See here, 60 mole percent of potassium pentoxide P2O5. Next 15 mole percent of ZnO, zinc oxide. Next 5 mole percent of aluminum oxide. Next 10 mole percent of barium oxide. Next 10 mole percent of lead oxide. Next X mole percent of terbium oxide. This is the different concentration of terbium oxide from 1 mole percentage of terbium and 2 mole and 3 mole, 4 mole and 5 mole. These are the different mole percentage of concentration of the Tb3 ions. Next, this is the experimental technique how we are preparing the glass material by using the electrical furnace but the method is called conventional melt quenching technique. So glass materials prepared by the conventional melt quenching technique. Before taking the melt process, we need to take the previously mentioned these chemicals: P2O5, zinc oxide, aluminum oxide, barium oxide, PbO and terbium oxide. These are in weight percentage we have to take, and that weight is we are 80 to 25 grams of weighing. By using the optical balance, we have to take the chemical composition. That chemical composition pour into this is the agate mortar to crush the chemicals to fine powder. So that is in micro size is there that we have to fine powder, that is in nano size powder we have to make it by using the agate mortar. After making the fine powder, we have to put into the platinum crucible. So this is the lid. Platinum crucible pour into chemical. After that, we have to cover with a platinum lid. After that, that completely chemicals we can keep into the electrical furnace at the melting temperature of 1250 degrees centigrade. For duration is 60 minutes, means for 1 hour duration we have to keep at the temperature of 1250 degrees centigrade. After melting completed, we have to pour into the preheated brass mold. This is the preheated brass mold. After that, this is we have to keep into the annealing furnace. That is at the temperature of 380 degrees centigrade. We have to keep. Time duration is 12 hours. So 12 hours we have to half day we have to keep into the annealing furnace. After coming to the 380 degrees centigrade to room temperature, at room temperature 40 degrees centigrade or 35 degrees centigrade. After we have to take it out and glass sample. After taking the glass sample, we have to cutting pieces, small pieces as per our desired pieces. We have to cut and well polished with both sides. Then after send into the different kind of calibration purpose. First, inside we need to measure the XRD. So XRD profile shows the whether prepared glass samples shows the glassy nature or crystalline nature. So you have to confirm with XRD profile glassy nature or crystalline nature. After measuring the XRD profile, we are getting the all observed peaks are broad peaks. You are not getting any sharp peaks. So this is shows that the prepared glass sample shows the glassy nature. So after confirm the glassy nature, we need to measure the different kind of characterization techniques. So experimental technique methods characterizations. That is first absorption. So absorption spectra characterized by using the Perkin-Elmer spectrometer. That is a model number is lambda 950 in the wavelength range of 250 to 2500 nanometer. That is optical absorption spectra. Again, fluorescence and decay measurements were carried out by using the Jobin Bayan fluorolog 3 spectrophlorimeter using xenon arc lamp as a radiation source. So you are using the xenon arc lamp as radiation source. The excitation of the sample is 394 nanometer. All the measurements were made at room temperature. So all the absorption analysis and fluorescence and lifetime measurements, all measurements are carried out at room temperature only. So these are the calibration techniques of the spectroscopic behavior of terbium-3+ group zinc phosphate glasses. Next, coming to the first result and discussion. First, we are analyzing is optical absorption. From the optical absorption spectra, this is a 5-8% of terbium-3+ ions. The UV visible, A is the UV visible region, and B1 is the NIR region, near infrared region. See, in the visible region, we are getting 1, 2, 3, 4 peaks from ground state 7F6. So ground state of the terbium-3+ ions from ground state 7F6 to different excited states. So we are observing 4 absorption bands in the UV visible region, and if you see the NIR region two absorption peaks are observed from ground state 7F6 to 7F012 and 7F6 to 7F3. These are the NIR region absorption transitions of the terbium-3 plus doped zinc phosphate glasses. This concentration of terbium ion is 58% of terbium-3 plus ions. Next, coming to the optical absorption spectra, what kind of data we are observed in the optical absorption spectra? See the room temperature optical absorption spectra of glass is UV visible and near infrared spectral regions were shown in the figure A and B respectively. As shown in figure 1, see the as shown in figure 1, the absorption peaks centered at 352, 358, 368, 378, 484 nanometers are assigned to the transition from the ground state from 7F6 to different kind of higher excited state, that is 5L. This is transition of the excited transition of the terbium-3 plus ions in zinc phosphate glass, that is 5L9, 5G5, 5L10 and 5D3 and 5G6 and 5D4 respectively of the 4F8 configuration of the terbium-3 plus ions. So we are getting the visible region from the ground state 7F to different higher excited state levels. The transitions we are assigned here. Next, in the NIR region, we are observed two peaks. That is, one is wavelength 1894 nanometer and 2223 nanometer due to transition from the ground state 7F6 to different excited state levels. That is 7F012 and 7F6 respectively. These are we are observed from the optical absorption spectra. From the absorption spectra, it is noticed that the bands corresponding to the 7F6 to 7F0 and 7F6 to 7F1 and 7F6 to 7F2 transitions overlap. The absorption band intensities are determined in terms of experimental oscillator strength F experimental and JO parameters following references. By using this from 5 to 8 references, we have calculated the experimental oscillator strength of the terbium-3 plus ions as well as JO, that means Judo offset intensity parameters also we have calculated by using the optical absorption data. From optical absorption data, we have calculated the JO parameter, that means Judo offset intensity parameters. In our present class, we source the JO intensity parameters omega 2, omega 4, omega 6. The JO intensity parameters are 3. That is the omega 2, omega 4, omega 6. In our present study, terbium doped zinc phosphate glasses, we are observed omega 2 values are 7.75 is omega 2, omega 4 is 1.13, omega 6 is 3.29. So these are the omega 2, omega 4, omega 6 of the JO intensity parameters of terbium-3 plus doped zinc phosphate glasses. These values we are comparing with different host systems, that means oxyfluoride silicate glasses, borosilicate, next phosphate and sodium fluoroborate and fluorophosphate and barium aluminum phosphate glasses. These are different. We are comparing with our present study different kind of host systems. In our present study shows the order of omega 2 is greater than 2, omega 6 and omega 4. That is, in the present study class, the JO intensity parameters follow the trend is omega 2. First highest is omega 2, next highest is omega 6, next omega 4. So this belongs to this omega T is more, omega 2 value is more compared to omega 4 and omega 6. That is why terbium-3 plus having the higher covalency around the terbium-3 plus ions. The magnitude of omega 2 is not only an indicator of extent of covalent bonding, but also explains the local structure of rare Re3 plus ion site. That means in the rare 3 plus ion, in particularly we are discussing about terbium-3 plus ions. So this having the higher covalence. So because we are having the magnitude of omega 2 value is higher than to the omega 4 and omega 6, because it's having the 7.75 value. That is why it shows the higher covalency, but not only explain the local structure of the rare earth ions also. That means terbium-3 plus. If compared to other terbium-3 plus systems in the table, see the present glass shows the higher value omega 2 that indicates the higher terbium and oxygen covalence and higher asymmetry around the terbium-3 plus ion site. That means around the terbium-3 plus to terbium-3 plus ion site, it will be higher asymmetry, at the same time higher covalence. That indicate the omega 2 values, higher value of omega 2. Next, coming to the excitation spectrum of terbium-3 plus doped zinc phosphate glasses. This is the figure shows the excitation spectrum of zinc borophosphate glasses mounted for the emission at 540 nanometer. Here monitoring the emission at 540 nanometer. Okay, so emission is 540 nanometer. This is the from terbium-3 plus and 7F6 ground state to different excitation. This is excitation spectra. So we are observing higher excitation values and excitation transitions. See, the figure shows the excitation spectrum of the terbium-3 3+ doped zinc phosphate glasses measured by the monitoring the green emission of Tb3 ion at 540 nanometer. As it can be seen, it is compared to two intensity peaks from F to F transitions. A broad band centered at 376 attributed to the superposition of 7F to 5D3 and 5D3. We are taking this broad emission. The higher intensity of the broad emission we are getting at the 5D3 level. So this transition we are used for the pulping purpose. We are using the emission analysis. We are using this transition, and also we are observed the one excitation band at 284 nanometer can be assigned to the spin forbidden 90 level 4F8 to 4F7 5D1 transition of Tb3 ions. So one additional band, that is 285 near this is the 4F to 5B transition also we are observed. Among this transition, 5D3 5G6 transition is found to be most intense. So this transition will be most intense from the 275 nanometer to 525 nanometer in the excitation spectrum. We are observing the highest intensity of the excitation peak is 5D3 to 5G6 transition. So that transition found to be most intense, which will be excited to the record the emission spectra of the terbium-3+ dope zinc phosphate glasses. So this transition we are going to use the for pumping purpose to measure the emission transition of the terbium-3+ ions zinc phosphate glasses. Next, coming to the emission spectra. That is why we are using the most intense peak, that is 376 nanometer of the 5D3 5L6 transition, that we are measure the emission spectra of the peak intensities of the 5D4 to 705 emission transition under the 376 nanometer excitation. So this is the emission spectra of the terbium-3+ dope zinc phosphate gases and different concentration weight percentage of terbium-3+ ions, starting from 1 weight percentage to 5 weight percentage of terbium-3+ ions. This luminescence spectra demonstrated the emission transitions arising from the both 5D3 and 5Y. These are the 5D3 levels and 5D4 levels. This is from 400 to 525 nanometer. We are observing 5D3 emission transitions. From 525 to 615 nanometer, we are observing the 5D4 transitions. So in terbium-3+ ions, we are getting the two important emission transitions from the 5D3 to different transition and 5D4 also. So here it is observed that the emission intensity of 5D3 state decreases with increasing the terbium-3+ ions. See here, if 5D3 to 704 this transition, if you see here, if you are increasing it, they observe that the emission intensity 5D4 state will be decreasing with increasing the concentration. So that intensity will be decreasing while increasing the concentration of the terbium-3+ ions that we are observing in figure. This should be due to the concentration pinching of the 5D3 level emission. So that is the pinching of 5D3 level of the terbium-3+ ions, which is more prominent for higher terbium-3+ ion concentration because of the reduction in the interionic distance. This is mainly due to the reduction in the interionic distance of the terbium-3+ ions. That is why the concentration pinching takes place in the 5D3 transitions of the emission transitions. Next, coming to from the emission spectra only, we are calculating the different radiative properties of the peak wavelength lambda p nanometer and radiative transition probability ER values, branching ratio BR value, branching ratios, that is the BR value. Next, delta effective, that is effective bandwidth and stimulated emission cross section sigma emission values, and sigma emission in lambda f, that is the gain bandwidth parameter. This is the gain bandwidth parameter, sigma emission into effective wavelength for the different transition from 5D4 to 7F3 to 6 transition of 5 mole weight percentage of terbium dope zinc phosphate glasses. So these are the 5D4 transition of the emissions we are observing: 690 nanometer, 582, 540, 486. Among all the transitions, we are 540 transition here, the intense transition we are observing. So that value we are getting more value. See, emission cross section, stimulated emission cross section value is 11.39 into 10 power of minus 22 centimeters square. This is the highest stimulated emission cross section value we are observed among the 4 transitions. We are observing the 540 nanometer is the highest stimulated emission cross section. At the same time, each and every parameter will be higher comparing to other terbium-3+ emission transitions. This stimulated emission cross section we are calculated by using this formula: lambda p4 by 8 pi cn square delta effective and ER values. So this calculated branching ratio in our calculated branching ratio is 0.76 for the 5D4 to 5 transition of 58% of T3 plus ions suggests its suitability for green color display devices. The higher value of stimulated emission cross section sigma emission is also favorable for low threshold and high gain obtained to continuous laser action. That is why we can use for the green laser applications. We can use for the CW lasers. That means continuous wave laser. That means CW lasers we are using for the terbium-3 plus doped zinc phosphate classes. These are the one of the important application in the case of terbium-3 plus doped zinc phosphate classes because it's having the higher stimulated emission cross section value, at the same time a higher branching ratio, at the same time delta effective also bandwidth also higher compared to other terbium-3 plus transitions. That is why we are using for the terbium-3 plus doped classes for the green laser applications. Next, lifetime or decay time measurements in the terbium-3 plus doped zinc phosphate classes. So this is the 5D4 emission lifetimes. So 5D4 emission transitions shows the each and every concentration lifetime will be constant. That means it shows the single exponential nature. So each and 1 terbium to weight percentage of terbium-3 plus doped glass showing the 2.94 milliseconds and 2.88 and 2.66 and 2.69 and 2.6. This is almost constant for the 5D4 transition because here energy transfer is not takes place because it shows the if decay curve is well fitted with single exponential nature. That is the 5D4 transition of the terbium-3 plus ions. In the case of 5D3 transition of the terbium-3 plus ions, if you see the concentration from low concentration 1 terbium weight percentage to 5 mole weight percentage, the concentration increases, lifetime will be decreasing very slowly. That means first see the 1 terbium weight percentage of terbium ion is 0.93 millisecond, next 0.77, 0.70, 0.50, 0.42. So this is from concentration increases, lifetime will be decreasing from lower concentration to higher concentration. That is shows the if you see the first concentration of the terbium ion is single exponential. After that, it turns into the single exponential to non-exponential nature. This non-exponential nature is well fitted to the IH model, Inoue-Hirayama model. That is the IH model. So by using the lifetime measurements, we are calculated by using the integral of T I of T dt equal integral of I of T dt. So this we are going to calculate the decay time measurements. By using this non-exponential nature, we are well fitted with the IH model S equal 6. By using a IH model, we have calculated the energy transfer parameter Q also. The energy transfer parameter Q. That is, you see in the insert diagram, so the terbium-3 plus concentration versus energy transfer parameter. Increasing the terbium concentration, energy transfer also increasing. That is the source the energy transfer takes place in the case of 5D3 transition of the terbium-3 plus ions. Next, this decay time measurements only we are calculated as a IH parameter. That means Inoue-Hirayama model. That is Inoue-Hirayama model. IH model is well fitted for the 5D3 transitions. That equation is the I of T equal I naught exponential of minus T by T naught. T naught is the lower concentration of the terbium-3 plus ion. Q is the energy transfer parameter. S is the order. S equal 6 means dipole-dipole interaction. If S equal to 8 means dipole and quadrupole. S equal 10 means quadrupole to quadrupole interaction. But in the case of in our present study, it shows the S equal 6. So our study energy transfer parameter Q value and its transition takes place from the dipole to dipole transition. So these are the table shows the concentration and experimental value here when next tau experimental values and concentration N naught, Q value energy transfer parameter R naught and CDA value of the terbium-3 plus doped zinc phosphate classes. So this pinching of lifetime and its non-exponential nature could be due to the increased energy transfer process through cross relaxation channels. That is the mainly due to the energy transfer takes place. That is Q is the energy transfer parameter that is takes place due to the cross relaxation between the terbium-3 plus ions. In order to find out the nature of the energy transfer process, we are using the Inoue-Hirayama model, and by using the fitting, we have calculated this energy transfer parameter Q values for the different concentration of the terbium-3 plus ions, in particularly 5D3 transition to 5F4 transitions. This is very important. Let's coming to the partial energy level diagram of the terbium-3 plus ions in zinc phosphate classes. So this is the energy level diagram. See terbium 3 plus ions to terbium 3 plus ions. See the here. This is CR means cross relaxation channels. That's a resonant energy transfer. This is RET means resonant energy transfer takes place from this level 5D4 to 5D3. This transition, this level energy band gap, this is 5794, and this level band gap, energy band gap 577, almost similar. So whenever the energy band is similar to the two transitions, automatically energy transfer takes place from 5D3 to 7F6. So these are the this is the cross relaxation results from the resonant energy transfer RET through 5D3 to 5D4, 5D3 to 5D4, and 7F6 to 7F6. This transition there. So this one and this one, because these both energies are similar. So almost this is 5778 centimeter energy band gap energy delta E. Here delta E 5794. So almost similar. So that is why energy transfer takes place from this level to this level. This is called resonant energy transfer in the case of terbium 3 plus dope zinc phosphate classes. So this matches well with the energy gap between 7F2 to 7F0 energy levels. This process becomes more prominent at higher terbium 3 plus ion concentrations. This cross relaxation by RET occurs among the excited active ions and its nearest neighboring unexcited active ions. That means near means the ground state near. This is excited atoms. So this level and this level is well matches with the energy band gaps. That is why energy transfer takes place through cross relaxation channel. That is the resonant energy transfer. So in the particularly this is the terbium 3 plus ions in zinc phosphate classes, partial energy diagram of the terbium 3 plus ions. Next, coming to the conclusion or summary of the present study. In summary, the concentration dependent luminescence of terbium 3 plus dope zinc phosphate glasses prepared by the conventional melt quenching technique was studied through absorption, excitation, luminescence, and lifetime decay time measurements were carried out in the present study. Next, two prominent green emissions are observed. One is 5D4 to 7F transition at 540 nanometer transition. The other one is 5D3 to 7F4 transition, that is a blue transition, that is a 434 nanometer emission bands are observed upon the excitation of 376 nanometer. It is observed that the 5D3 emission intensity of terbium 3 plus ions decreases with increasing the terbium 3 plus concentration, with intensity of green emission from 5D4 level as shown a linear increases. In the 5D3 only we are observed that is a blue transition, we observe the decreasing, while increasing the concentration, luminescence intensity will be decreasing. In the case of green emission at 5D4 transition, it will be almost linearly increases. Next, decay curves of the 5D4 level of terbium 3 plus ions exhibit single exponential nature for the all the concentration, and lifetime vary slightly from the 294 milliseconds to the 2.62 milliseconds. The 5D3 fluorescence decay curves have shown non-exponential nature for all the concentration. That non-exponential nature is the well fitted to inocuity Hirayama model. By using that inocuity Hirayama model, we have calculated the energy transfer parameter also. Finally, the radiative properties of 5-8% of terbium 3 plus dope zinc phosphate glasses strongly suggest that utility to develop the green color display devices and solid state visible lasers. Solid state visible lasers we can develop by using of terbium 3 plus dope zinc phosphate glasses. That is why we can use for the terbium 3 plus dope green laser applications we can use. That is why our topic is spectroscopic behavior of terbium 3 plus ions in zinc phosphate glasses for green laser applications. This is a unique property in the case of terbium 3 plus ions. These are the summary or conclusion of the present study. Next, these are the cited reference of the in the present study. See, this is the different references. The 7th and 8th reference and the 6th reference. By using this 6, 7, 8 reference, we have calculated the oscillator strength and also Jude of rate intensity parameters. And 10th citation is used to calculate the energy transfer parameters and interaction parameters Q and CDA values by using the inocuity Hirayama model. Next, this paper is published in the reference 9, that is the Journal of Luminescence in the year of 2015. These are the important references in the present study. Finally, thank you. So next class we will continue with the other topic. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.